All right, so we're hopping around the beginning of chapter 2 a little bit, just like we did in chapter 1, because we have to talk about this concept of differentiability, which is covered back in section 2.1 in our textbook. So let's read a little bit here. It says a differentiable, a lot of syllables there, a differentiable function is one in which we can find a specific value for the derivative at any given x value. We say a function is not differentiable whenever the derivative does not exist. So there are places where a function is not continuous. And obviously, if it's not continuous, like at a hole, an asymptote, the vertical kind, or a jump discontinuity, all of these places it will not have a derivative. There's also places where a function is continuous, but it doesn't have a derivative. And this is the hard part that we're going to look at today. So these not so obvious places are probably a bunch of new vocabulary to you. We're talking about cusps, corners, and no short way to say this, vertical tangent lines. And that one kind of probably makes sense if you think about the slope of a vertical line, right? It's undefined, so we're not going to have a derivative there. So we're going to look at these three in more detail down here below. So let's look at this first one, which is addressing the idea of what a corner is. So if we're going to look at what a corner is, we're going to probably graph this piecewise function that we're presented with. It looks like sine when it's less than or equal to 0. So if I plug in 0 right away, it goes through 0. And then it looks like the sine curve, right? So it's going to go through pi and 2 pi here. So it's going to kind of look like this. And then the x squared side of it, right? Oh, this should be a greater than. Sorry. So it's x squared when x is greater than 0. If we plug in 0 to x squared, we get 0 also. And then, of course, it looks like this parabola attached here. So I know that this area right here looks like a nice smooth value, but we're trying to find out if this is a corner. Okay, we can't rely on what our human hands can graph. We have to do a little bit more of analytical analysis. So let's start by, this function is continuous, right? But we're just not sure if it is differentiable. So we're going to take the derivative, which is going to look like a piecewise function also. So the derivative of the top, derivative of sine is cosine x when x is less than or equal to 0. And it is x squared when x is greater than 0. Oh, fail, teacher. Take the derivative, shall you? So 2x when x is greater than 0. And what we want to do is we want to find what we call the left-hand derivative and the right-hand derivative. So the left-hand derivative is what we get when we plug in when we plug in 0 to cosine, and we get cosine of 0 is 1. So that means the slope right here on this side of things is 1. And now the right-hand derivative, we're going to just estimate, f prime of 0 in the other piece, right? So now we're going to plug it into the 2x. And there, of course, I get the slope of that parabola is actually 0 on this side, right? I would have a horizontal tangent line if you think about the way a parabola looks, right? You would have that vertex there and the tangent line would be horizontal. So because of that, because these two values are in disagreement right here, we would say that this function is not differentiable. At x equals 0. Okay, this is technically a corner. I know that when you picture a corner, you picture like a 90-degree angle, but this is a corner because of this rough transition from a slope of 1 to a slope of 0 right at the origin. Okay, so all corners are going to have two different slopes. in order for the function to not be differentiable. All right, let's take a look down here in this cusp example. We've got the graph. The suggestion here is x to the 2/3. Now, we probably haven't studied this very much, but I would like to argue that we want to remember that this is the seagull graph, right? Remember the first bird you ever learned to draw when you were little? So this graph goes through the origin, right? 1 to the 2/3 power is 1. And what else do we know about this function? I guess 8 is probably the next value. 8 to the 2/3 power. It doesn't really fit on here. Is 4. So 8 would kind of be somewhere off here. So we kind of go off the grid a little bit here. But so this is what this function looks like. Oh, heck no. Okay. So it looks like a big fat seagull. And the cusp that we are looking at is right here at the, excuse me, origin again. Yeah. So let's think about what the derivatives are doing on the left-hand side of this function and on the right-hand side. So let's see, what's some good colors for this? Let's do the red side here. If I'm picturing little teeny tiny tangent lines all the way along here, and we can see that these tangent lines, as we move towards the origin, right, got steeper and steeper and steeper in a negative direction. So we would say this left-hand derivative is negative infinity as we approach 0. The right-hand derivative, again, picture little teeny tiny tangent lines all along the way. They're also getting steeper and steeper and steeper as we approach 0 from the right-hand side. So we would say the right-hand derivative is positive infinity. Okay, and again, like before, because the left-hand derivative and the right-hand derivative are two different values, right? This disagreement down here leads us to say that this function is not differentiable at 0 either. But this is a very specific case. A cusp is when the derivatives, one side is approaching negative infinity and the other side is approaching positive infinity. Okay, so this happens a lot of times, like, I don't know, x to the 4/3 is probably the same. Actually, I'd have to take a look at that. Maybe x to the 5/3, I'm not sure, but these might have similar features on them. Okay, and then the vertical tangent line is the last sample we have to look at here. So the vertical tangent line, the suggestion here is is the cube root of x, which we should know is x to the 1/3 power, and that is the inverse of x cubed, right? So we know that x cubed, looks like this, and the inverse of it is going to just be rotated, right? So the inverse for x to the 1/3 is, more animal references, is a snake function. So it goes through 0, 0, it goes through 1, 1. And then, again, not till 8, it goes through 2, and -8, it'll go through -2. So let's see how good I can draw this. So slithery snake is always what I picture here when I picture this function. So in any case, this slithery snake, if I think about those tangent lines like I did on the last example, if I'm approaching the origin here, this is where the vertical tangent line exists, right? All of these values, right, are approaching what we would say is infinity there on the left-hand side. So they approach infinity. And unlike a cusp, if I approach and look at these tangent lines from the right-hand side, they also approach infinity, these little tangent line slopes. Now, this is the first time we'll notice that these two actually agree, right? But if we think about what I had kind of said at the beginning, a vertical tangent line does have an undefined slope. And since that is not definable as a number, the undefined slope at that point of 0 means that we are going to have no differentiability right there. Okay? So x to the 1/3, x to the 1/5, x to the 1/7. It's a lot of those odd fractional powers. Okay? The other thing you could look at here is if you took the derivative, brought that power down, decreased it by 1, right? You would have 1 over the 3 would stay there, and then the x to the negative 2/3 would be the cube root of x squared. And if you actually took this denominator and set it equal to 0, right, we would divide by 3, cube both sides, square root both sides. The only solution we get here is 0. So there is a finite way. If you take the derivative and figure out where it does not exist, right, you will have the value where the point of non-differentiability is. Okay, so let's look at just some other cases here. It says if f of x is this function in example 1, we want to know, is it differentiable at 2? And a lot of times they'll ask you, is it continuous and differentiable? So we can start off with a graph of this because it's pretty reasonable to graph these two functions. X squared plus 1 less than or equal to 2. If I plug in 2 right away, I get 5. And then I know the rest of my parabola, right, kind of looks like this. And then the 2x plus 1 part, if I plug in 2, I also get 5, right? So my slope there, though, would be 2 up and over. So the question is, right, is what is happening right here? It is continuous, right? So if we're checking the boxes, we know that this function is continuous. But now our question is it differentiable? So we have to take a look at these slopes like we did before. So let's take the derivatives. We get 2x for the top part, and we get just 2 for the bottom part. And then if I plug in 2 to each of those, the top derivative is 4. The bottom derivative is unchanged because there's no variable there, right? It just stays 2. And so what we're seeing here is that the parabola at that point actually has a slope of 4. And that the line, of course, we know has a slope of 2. So since those are in disagreement, we would say it is not differentiable. Okay, and then let's look at this case over here, example 2. We have e to the x graphed less than 0, and then x plus 3. So we're going to check the same two boxes. Is it continuous? Is it differentiable? Right, so e to the x, probably been a long time since you graphed that, kind of looks like this, right? It's an exponential function. I'll try to draw that a little bit better here. So it goes, I'm plugging in 1, e to the 1 is 2.718-ish, right? That's the value of e. E to the 0 power is 1. And then we know it's asymptotical along this x-axis here. So actually all I can see of the e to the x function is this much, rather uninteresting. Now I need to graph together with that at 0 is the function x plus 3, right? So that half of it, right, just has a y-intercept of 3 and a slope of 1. Okay, now what this particular function is, and also I guess if I'm being super particular, oh dear, it should have an open circle here because of the less than 0 up here, and it looks like this. So we know that this function is not continuous, right? Because f of 0, if I think about that, gives me e to the 0 power, which is 1, and 1 plus 3 gives me 4. So not 1, man, like 0 for a million tonight. 0 plus 3 is 3. So this function is not continuous at all. And since it's not continuous, it's definitely not going to be differentiable. So that's enough for you to say not continuous or differentiable. What's weird about this one, and the trickery here, is that if you were to take the derivative, right, of this particular function and establish f prime, right? The derivative of e to the x we know is e to the x, and the derivative of x plus 3 is 1. If you plug in 0 to each of those, you get e to the 0, which is 1. And of course, 1 is unchanged. So this part and this part actually have the same derivative. The slope is 1 on both of those functions. But since it's not continuous, we cannot say that it's differentiable. And that kind of leads us to this theorem here. It's a very poetic, very romantic theorem. So it goes a little something like this. Roses are red, violets are blue. If f is differentiable, it's continuous too. So a little romantic poem from me to you. Now, remember that a function can be continuous but not differentiable. But it can never be differentiable but not continuous. So if you can find a tangent line's value, the slope of it, then you can go ahead and assert that that function is continuous. So this is a nice theorem for us to look at. All right, last one here is, I'm going to do example 3 with you and then have you guys try example 4. When we get stuck talking about differentiability and continuity together, we see more of these piecewise functions with these missing values here, some constants that we need to figure out. So this is very much like the ones that we did in the last unit for continuity, but now we have to bring in the differentiability piece as well. So here I'm stealing the idea from chapter 1. So I'm going to write a continuity equation with the x, well here, I'll write it in its basic form. So continuity would guarantee that one side equals the other, and more specifically, right, one side would equal the other when I plug in 1 for x. So I'm going to plug in that breakpoint of 1 to both functions here and get 1 minus b, or carry out my orders of operation, equals a plus 1. So I'll probably just solve for a here because I'm going to do some sort of substitution. And it looks like negative b equals a. Okay, so I know I've got 2 variables to solve for, and systems of equations tells me that I'm going to have 2 equations then if I'm going to solve that, right? So after you write your continuity equation, we have to come up with our differentiability equation. Differentiable. So that comes from taking the derivative, right, piece by piece, like we've been doing in this whole video, 2x minus b. Now this is the weird part, right, is that if we have a derivative that says x squared minus bx, we have to imagine that that b value is a constant, right? So when we differentiate a linear term like x, its derivative is just its constant. So that's why the derivative of x squared minus bx is 2x minus b. And then when we differentiate ax squared plus b, we're going to bring the 2 down front. It's going to multiply by the a, because that constant will stay with us. So I'll have 2ax for the derivative of the second piece, right? Because the plus 1, that is a constant, so the derivative is 0. So now I'm going to set these 2 equal to each other and plug in 1 for x. And come up with this information for my second equation, right? And so now what I'll do is I'm going to take and use substitution to solve this. So I'm going to put negative b over here for a and subbing. So I'm going to write 2 minus b equals negative 2b. So why don't we add b to both sides? 2 equals b. Nope, 2 equals negative b, which means positive b equals negative 2. And then I'm going to go back and sub this in over here. So the opposite of negative 2 is going to equal a. So a is positive 2. And you can try example 4 on your own.